If you've ever worked with a magnetometer, you might realize how much of a pain it is to get these things to work as a digital compass. If I compare it to my phone here, you can see I'm lining it up and my direction of heading should be this way. And it doesn't seem to matter kind of how much I turn. I can't get that 153. Oh, wait, here we go. 153 is not even here. That's because this magnetometer has not been calibrated, and we're also not applying magnetic declination to convert magnetic north to true north, or a magnetic heading to our geographic heading. I'm going to show you how to calibrate your magnetometer as well as apply magnetic declination so that we can get a magnetometer working as a much better digital compass. Let's get started. The two main settings we care about are hard iron calibration and soft iron calibration. I'll go through both of these in this video so that you can get a better understanding of how to use your sensor and get relevant or useful data out of it. The other thing we care about is magnetic declination. This is the value we get from a compass or digital compass that helps us get our heading as related to the magnetic north and south poles of our planet. If you want to convert that information into a geographic heading, as determined by the geographic north and south poles, we have to do a little bit of math to make that conversion. Let's say that we have a magnet that exerts some force on other magnetic material, or ferrous material. For our purposes, we'll assume the Earth acts like a basic bar magnet. We can visualize this force as a vector field. The strength and direction of the force at any point depends on how far away from the magnet you are and your relative position to the magnet or the poles of the magnet. We can use a magnetometer to measure the strength of this field. A 3-axis magnetometer, like the one I'm using, gives us the strength of each of the X, Y, and Z components. From that, we can determine the direction and strength of the field at any point in space. If we keep our sensor parallel to the ground, meaning the Z-axis points directly up into space or toward the center of the Earth, we can calculate the heading by taking the inverse of the tangent of x over y. This has the y-axis pointing toward our heading. You can flip x and y if you want to have x pointing toward the heading. Note that most heading values are given in degrees, so you'll likely need to convert from radians to degrees. You might need to multiply the result by -1 depending on if your z-axis is facing toward the sky or toward the ground. With y as our heading and z pointing toward the sky, we'll want that -1. I have my system displaying the raw X, Y, and Z magnetic field values in microtesla. Hard iron distortion occurs when there are permanent magnets in the area. Keep in mind that these could be in nearby speakers and motors. This causes a simple additional bias to the X, Y, and Z values, which you can see occurring on the screen here. To correct for this, we measure this bias and subtract those values from our raw readings. Soft iron distortions occur due to the presence of objects that bend or warp the existing magnetic fields. Ferrous materials like iron and steel is notorious for introducing soft iron distortions. We have to do some complex math to compensate for soft iron distortions, but luckily we have some tools to help us out. Electronics contain a bunch of ever-changing currents, which produce magnetic fields. These can be nearly impossible to accurately model, and it's not something I'll get into here. To make it easy, I recommend performing hard and soft iron calibration with your magnetometer once you have it enclosed and mounted. This includes having any nearby electronics running that you might use. To start the calibration process, we're going to need to collect raw magnetometer data from a sensor. In this case, I'm going to use an Adafruit breakout board that contains an LIS 3MDL magnetometer, and that has 3 axes, as you can see given by the graphic here. We don't need an OLED for this, so I'm just going to remove this component, and I'm going to connect it to an Arduino board over I2C. I'm using Quick or Stemma for this, so feel free to make your connections. Note that I'm using the Adafruit libraries for this, and their sensor lab libraries don't work very well with something like an Arduino Uno or anything based on the 328P or 32U4, so you need to use something a little more powerful. This is mainly due to the fact that it requires a lot of flash space, so I'm going to be using a SAMD21 chip, and this is a Feather M0 logger, but you don't really need that. This is just the board I had available. Go ahead and connect everything up, plug this into your computer, and let's head over to Arduino. You're welcome to use any language you'd like on any board you'd like. The main thing is we need to get raw data, generally in microtesla, captured from the magnetometer and sent over to another computer program that will perform the calibration process for us. I'm going to use Arduino because it's easiest, and Adafruit has a number of nice libraries to help us out. To use this board, you'll want to go to your board manager URLs under File Preferences and make sure you add the adafruit.github.io board index to the list of board manager URLs. Once you've done that, go to your board manager, search for Adafruit SAMD boards, and you'll want to install the latest version of this. For me, 1.7.8 is what worked. Install that, and then go to your Include library under Sketch, Manage Libraries, and search for the Adafruit Sensor Lab. You'll want to install this. I used 0.7.1. And then we want File Examples. Look for the Adafruit Sensor Lab Calibration, and you want IMU-Cal no save. Note that this was originally written for IMUs, or 9DOFs. We just care about the magnetometer version of this. This will work with that particular magnetometer I just showed you. It just won't read your accelerometer or gyroscope, because those aren't attached to the board, but this will work anyway. All it's going to do is connect to the magnetometer. It'll try to connect to a gyroscope and accelerometer if they exist, otherwise it just ignores those. It will get the event, and this contains sensor data. It's going to convert those to microtesla and send them out in two different formats, in this case raw and unified data. I'm going to start the upload process. Make sure you have your board selected. This is the SAMD21 board, COM13, that looks good. I'm going to upload this. Motioncal is a computer program from PJRC that will look for data coming out of the serial port in this particular format with this raw header. It will take that and then do the calibration for you. We just care about the magnetometer information here, which I believe is microtesla times 10, so that you can get a good integer value. Other programs like the Jupyter notebook that I'll show you use this unified format where it just comes out in pure microtesla format without multiplying by 10. Once it's done uploading, you can open the serial monitor and you can see this information flying by. As you can see, the raw format is an integer version, that's the microtesla times 10. The unified is the actual floating point value, so that's how these two are related. The two programs we'll look at will read these values in their raw format, parse them, and then use them for calibration. Notice that our accelerometer and gyroscope data is 0 for these cases because the calibration programs we'll use, we'll just ignore them for now. We don't care about calibrating with them. They are useful if you want to fully calibrate an IMU for doing things like absolute orientation for something like a VR headset, but we don't care about that right now. Let's close out of this and we'll open up a Jupyter notebook. This Jupyter notebook was originally written by Adafruit, but I modified it a little bit so that we can see what's going on. The original one was used for hard iron calibration. We're not going to ultimately use this program for calibration. We're going to use that PJRC Motioncal because that does soft iron as well as hard iron. But this is a very useful demonstration to see what's going on in hard iron distortion. So let's skip past these. If you don't have matplotlib and PySerial installed, you'll want to uncomment this line and install them. Here are some imports. This is a magic command so that we can do animations in Jupyter Notebook using matplotlib. If you're using this, you'll want to set up, say, the port as well as the history size. We'll keep interval at 10 milliseconds. If the serial port is open, we'll close it. Make sure you've closed out of the serial monitor in Arduino, and we're going to open it again to that Arduino. If you see opened the serial port, that means it's working. This function is to capture some serial data from that IMU or the Arduino. In this case, we're going to ignore most of the IMU data and just use the magnetometer data. Notice here we're using the unified format, not that raw format. When you run this cell, immediately start moving your magnetometer in all different orientations. Pretend it's a model rocket ship or an airplane or something, and you're just trying to make it face every possible direction. We're collecting raw X, Y, and Z data, mapping them to a sphere, and then projecting that sphere onto 3 different planes so you can get an idea of what the X, Y, and Z coordinates look like. When you're done collecting data, you can push the stop button up here. Ideally, you'll want these circles filled in, but this is going to be good enough for now. Next, we calculate the ranges that give us the X, Y, and Z, the maximum and minimums for those axes. And then the hard iron correction simply takes that range and divides it by 2. That's all that's really going on, is you find that middle point between the minimum and maximum values for each of your X, Y, and Z axes. With this hard iron offset, you can then subtract that value, this bias, from your raw X, Y, and Z readings to get a correction for our hard iron distortions. And with that, our circles should line up with each other, and ideally, they should be more or less over 0, 0 for the center point. This gives you the hard iron correction values that you can start using in your program if you've mounted your magnetometer near some type of permanent magnet, like say a speaker. However, this doesn't help us with soft iron corrections. With soft iron distortions, these circles will start to appear more elliptical in one fashion or another along one particular axis. We need to do some complex matrix mathematics in order to find those correction values. I won't get into those here, but we will use a piece of software to do those corrections for us. Head to pjrc.com/store/prop_shield.html. Scroll down and you can find the Motioncal software to download. So download it for your particular operating system. I'm on Windows. I've downloaded it and install it, and it looks something like this. Before we go here though, make sure you reset your board, or you'll want to run the cell that's up here if you're still connected to your Jupyter notebook. This will close out that serial port. From here, we can now go ahead and run the Motioncal software, and we can connect to our board. Go to port, connect your board, and we're going to do this exercise again of moving this magnetometer around in all different positions. Try to move it in a sphere, facing all possible orientations, twisting it where you can, pointing it towards their different walls, the ceiling, the ground, moving it up and twisting it. And we're trying to get that gaps number to be below about 1 or 2%. All right, and that's probably good enough, so I'm going to say none. And we have our hard iron and soft iron calibration results here on the top right. These are the numbers you will want to use to plug into your program. To do that, I'm going to open up this mag calibration test, and I will make sure to put a link to all of this code that's going to be in a GitHub repository in the description of this video. This actually does the exact same thing we were doing before, where it just sends out raw and unified data to whatever program's listening to it, but it's going to apply hard iron and soft iron calibration to those results, and I'll show you what's going on here in just a second. Make sure we're not connected. I'm going to move that program over so we can see the calibration results. The magnetic offset is the hard iron calibration results. If you don't want any calibration, these should just be 0, 0, 0, as that subtracts 0 from all of your raw data. But I'm going to plug these in. So we have those stored, and we need to do soft iron. If you don't want any calibration for soft iron, it should be the identity matrix with 1 down your diagonal and zeros everywhere else. As you can see, it's very close to the identity matrix. There's not much in the way of soft iron calibration, as they're was no real ferrous material near the magnetometer. I honestly tried doing this with the file nearby, which is quite ferrous. However, because I couldn't hold it steady at a particular distance away from the magnetometer, these readings would be off regardless of where I tried to put the magnetometer. I couldn't maintain that distance to make this demo work nicely. But this should give us good readings in Motioncal as it is. If we scroll down, you can see that all we're doing is connecting to the magnetometer. We're going to print some stuff out to the serial port. In our loop, we're going to get the raw readings, which are stored in this event struct. This is just your X, Y, and Z. It should come in microtesla. We're going to apply these hard iron offsets. All that's happening here is we subtract the hard iron X offset from the raw X value, and we do that for Y and Z as well, and we're storing it in this hard iron calibration array. So 0, 1, and 2 is X, Y, and Z. We're going to use that in our soft iron scaling. There's a pretty good paper I found on soft iron calibration. It covers hard iron as well, but they demonstrate how to use the calibration data to get calibrated values. It's fairly straightforward matrix multiplication. We have our raw values, we subtract the hard iron offsets, which we've already done. So this term becomes our hard iron corrected values, and we're going to do simple matrix multiplication with our soft iron calibration values and these corrected values for hard iron. And all we do is multiply this first value by the value here, the next value by the next value, and we multiply this value by this value. We sum those together to get the soft iron corrected value for X. We're going to do the same thing for Y. So we add this term times this term plus this term times this term plus this term times this term, and that becomes our Y. We repeat the process for Z as well. So this bottom row multiplies by this vector and we get Z. So that's how we're getting our fully calibrated for hard iron and soft iron values from our magnetometer. And that's what this for loop is doing. It's just going through and performing that matrix multiplication. This mag data stores our corrected values and we're going to print those out. Let's go ahead and upload this to our Arduino, and we're going to head back to our calibration tool here. Once that's done, you can minimize out of Arduino because what we care about is looking at the values from this tool. Let's connect to our board, and we're going to do that exact same exercise where we move this magnetometer around in all different orientations, trying to get that gaps down to something below 1%. When you're done, my gaps are close to 1% or lower, which is fine. What you should see is that your magnetic offset, your hard iron offsets, are closer to 0. They're a lot better than they were. And your soft iron offsets, your magnetic mapping, these should be very close to the identity matrix, where it's 1 down the diagonal and 0s everywhere else. It's really hard to get these to be exactly that, but as you can see, this is fairly well calibrated, at least for my magnetometer in that particular position. Now, if I move it somewhere else, there are other magnetic fields going on, there are other soft iron effects, and these will change. This is why it's a good idea to always calibrate once you have your magnetometer mounted in the place you want it and running next to any of the electronics, because those will affect some of these values as well. From here, let's use this information to make a digital compass. I've already copied in the hard iron and soft iron calibration. This should match what we found earlier from running Motioncal. It lines up with these values. The other thing we care about is magnetic declination. If we were to use the hard iron and soft iron, so we scroll down here where we calculate the heading, and this is the equation I showed you earlier in that slide, assuming that Y is pointing in the direction of our heading, we can convert it to 0 to 360 degrees, and this would get you a magnetic heading where 0 degrees is pointing towards magnetic north. If we head to this really slick page on colorado.edu, you can see an animation showing how the Earth's magnetic field and poles move over the years. That's because the magnetic poles do not line up with the geographic poles. The Earth spins along the geographic poles, that's true north and true south. However, the magnetic poles don't exactly follow those, and in fact, they move quite a bit. In some areas along these declination lines, I believe they're shown in green here, magnetic north and south do line up with geographic north and south. So you don't need to care much about adding or subtracting that declination value. However, everywhere else, you do need to care if you want to convert from magnetic heading to a true or geographic heading. If you want your application to work like a compass would, you don't need to worry about this because a compass follows the magnetic fields, not the geographic ones or the geographic lines. But if you do care about true heading, then we do need to do this conversion. I recommend going to ngdc.noaa.gov/geomag/declinations.shtml. There's a magnetic declination calculator that you can find here. So click Calculate. You can find your latitude, longitude. I'm in New Orleans, so I'm going to type that in. It's going to give me the latitude, longitude. I'm going to click Calculate, and it gives me my declination value. Notice here that there's some plus or minus. We don't care much about that. We're going to go with this one value here. Also notice that it changes over time. So if you're making an application that's going to last more than a year, say for example, you might want to revisit this site to get new declination values. Or consider connecting something to the internet and with GPS, like a cell phone, that can automatically update your declination values to your application. That's how cell phones are able to do it. They have GPS and internet built in. They can automatically figure out where you are and calculate the magnetic declination values automatically without you having to enter them. But for our application, we need to do them manually. Let's bring up a calculator. Notice here that we have degrees and minutes. We want this to be in degrees with decimal degrees. We want it to be a floating point value, not this minutes stuff. So we're going to take 14, we're going to divide it by 60 to get 0.2333, and we're going to add 1. So this is our magnetic declination value. East, if there's an E here, that's positive. West is negative. So this is negative 1.2333 if I'm in New Orleans. Let's go back into our application and we're going to scroll up to where it asks for that magnetic declination value. We're going to enter minus 1.2333. You can keep going with decimals if you'd like, but that should be good enough. Remember that this is not going to be very precise because we're also not accounting for things like tilt on our magnetometer. And if I move around even within this city, this is going to fluctuate a good bit. This value, this magnetic declination value, is used, it is added to our heading once we calculate that in degrees, and then we convert it to 0 to 360 degrees. By default, this is going to give you something like negative 180 to positive 180. And when you talk about headings, it's usually 0 to 360. So that's how we do that calculation. If it's west, this is subtracted from heading. If it's east, it's added to heading. That's all we have to do for magnetic declination. Right now, this sample code is spitting out to an OLED, so you can see it when I show it to you on the camera. I will make sure to update this code for you so that you can enable or disable OLED so that it will print right to your serial terminal if you want to try it without needing an OLED. But for now, let's upload this to the board and see if our digital compass works. With the calibration data added, it's a lot closer to the heading that's given by my phone. Couple things to note here. One is as you move closer to magnetic material, ferrous material, or other electronics, you can see it really starts to throw off these values. So try to keep it away from new materials. If you add it to new materials or have it close by, you're going to need to recalibrate. The other thing is we are pointing towards a geographic heading, and that's the number being given here, which should line up with the geographic heading on my phone. As I turn the board side to side, it throws off that calculation. So be aware of which axis you are using to point towards your heading. So I'm using Y and then X for my calculation. So as X moves away from those field lines, it's going to throw off the calculation, which you can see here. Let's rotate my phone a little bit and see if it keeps up. So we'll point it directly south and make sure it's level with the ground. And sure enough, 180. And we'll keep rotating. You can see the compass moving there. 173 is about this way. And it's not going to necessarily be exact, but it's pretty close. Once again, it depends on how parallel I'm keeping this thing to the ground. Hopefully this gives you a start. Remember that wherever you install this, you will need to rerun your calibration and update the settings in your program. I hope this helps you get started with magnetometers and, as a result, using them as digital compasses. We didn't even get into tilt compensation. That's where you have an accelerometer on the same border plane as your magnetometer, and you use the information from that accelerometer to compensate for the amount of tilt or orientation that your board is in, so that you can use the magnetometer to get a heading regardless of that orientation. Have fun navigating, and as always, happy hacking!